Okay, hello again. We're moving on to section 18.2. I'm working with a new writing tablet today, so you'll have to let me know if you notice any differences. I haven't really noticed too many myself, but yeah, you'll have to let me know if the video looks different. So this section is on linear operators, and what you really want to think when it comes to linear operators is that these are just matrices in infinite dimensions, aka quote-unquote matrices on functions instead of vectors. So the same way that we had something like, okay, a matrix took in a vector v1 and an output a vector v2, we'll have a linear operator, which we often denote with an L, that's going to input a function and it's going to output a new function. And for these to be linear, the important part about linearity is they satisfy the same property of matrices, where if I took a linear combination, so this is how I'm going to represent a linear combination of two entries, v1 and v2, I recover the linear combination of the outputs of the matrix, bm v2. So that was common with matrices. With linear operators, the linear part of linear operators is the same situation, where we have something like a linear operator on a linear combination of functions, af plus bg, is a of l, a times l of f, plus b times l of g. That's what it means for an operator, this thing L, that's like a matrix in infinite dimensions, to truly be linear. And let's look at some examples of this. The first one the book shows is the x there. It's really saying, let's define an operator, L on f, and we'll define it as x times f. So is multiplication on the left of some function by x, is that a linear operator? And we can just check that multiplication by x on a linear combination of two functions is x on the first function plus alpha times x on the second function. So we get that this is a linear combination of, let's see, so x f plus a, or alpha in that case, xg, which is exactly what we wanted for multiplication by x to be linear. We can also verify that this actually maps the space of functions to itself, just looking at the Taylor series, that yes, multiplying by x definitely keeps you in the analytic function spaces. We're going to skip that for now because it's not too important. But the next really important operator, the whole reason why we're talking about linear operators here, kind of the entire reason why this theory has been developed, is that the derivative is a linear operator. So if I'm looking at the derivative on a linear combination of functions, that ends up being the linear combination of the derivatives of functions, right? So derivative of a linear combination is a linear combination of derivatives. That's what it means for the derivative operator to be a linear operator. It's definitely an operator because you start with a function, you end up with a function. So that's saying something like L of f being defined by f prime is linear. And that's really why it's important that we're studying these linear operators, because derivatives and multiplication by x are both linear operators, and these are both very common operations we like to perform. So if we can get some sort of similar behavior, I guess maybe I'll add a line here that says, the reason why we study these is to extract properties of linear algebra, and more importantly, matrices. Right? So matrices are maps on linear maps on finite dimensional spaces. We would like to extract those properties into differential equations. So the primary reason we study these is that we know that the derivative operator kind of behaves like a matrix on infinite dimensional spaces, and this, you know, that if you have an equation with a derivative operator in it, that's basically a differential equation. Can we treat differential equations like matrix equations, like linear algebra equations? And if so, what is the language that we need to use to describe differential equations, like a linear algebra equation, or like a matrix equation, so to speak? So can we use the same language of linear algebra and matrices, but with derivatives? That's kind of the most important thing we want to think about with linear operators. So a great example of maybe a more general linear operator that you would construct out of a linear combination of linear operators is the Hamiltonian operator that you've seen for maybe your Schrodinger equation. You know, you'll have something like h psi equals e psi. That's an eigenvalue equation. H hat psi equals e psi. This is an eigenvalue equation. akin to if you were to have mv equals lambda v in linear algebra, you want to think of lambda here like e, you want to think of m here like h, and you want to think of v like psi, but the top equation is just an equation in infinite dimensions instead. So somehow we have to link h hat, which is a differential operator, we have to link that with a matrix. We want to use the same sort of language to talk about both of them, and that's what linear operators allow us to do. Okay, so then jumping ahead, right, one section ago we kind of talked about adjoints, right, matrix adjoints, and we decided that the matrix adjoint was the conjugate transpose of a matrix. The question is do we have a similar language for linear operators? And we certainly do. So let's recall really quick that for a matrix, and instead of using M, I'm going to use the notation of the book now. So for a matrix A, its adjoint, which was denoted by A dagger, had the property that A V1 dot product V2 equals V1 dot product A adjoint V2. So what the adjoint does, so maybe I'll say in other words, the adjoint is the price we pay for moving matrices through dot products. Okay, it's the price we pay for starting with the matrix there in the dot product and moving it through the dot product across to the right. That's what an adjoint is. And the same is true for linear operators. So considering a linear operator L associated to an inner product, right? We're jumping into infinite dimensions, so we just generalize our dot product to inner products. The adjoint is the price you pay for moving it to the right in the inner product, or moving it through the inner product. So we do the same thing. We have the same language when it comes to linear operators. Let's look at the matrix adjoint really quick. This is an example where the matrix A is 1, 0, 1, 1. And if we define a vector U, U1, U2, and V, V1, V2, and we're thinking about, hey, I'm going to act the matrix on U and I'm going to compute an inner product with V. If we go through the work to compute that inner product, we end up with U1, V1 plus parentheses U1 plus U2, V2. Suppose we want to find the adjoint of A. That would be finding the matrix for which, if it's on the right-hand side instead of the left-hand side, and I compute an inner product, I get the same thing as I would have gotten if it were on the left-hand side. So let's think about computing this really quick. So if I have U1, U2 dot some matrix, A, B, C, D, for example, V1, V2, then what I need out of this matrix, this A, B, C, D matrix, what I need is a U1 times a V1. So I'll need U1 and V1. I'll need A to be equal to 1. I'll need a U1 V2, which means that I would need, I guess, B to be equal to 1. I'll need a U2 V2, which means D needs to be equal to 1. And I do not need a U2 V1, so C is allowed to be 0. So in fact, this should be my matrix A dagger, 1, 1, 0, 1, and you'll notice that's exactly the conjugate transpose of A. So we can compute that directly, or you can just use the property that it should always be the conjugate transpose. The rest of that example is the book doing exactly what I showed you. And then let's try this for maybe the whole reason why we're in this section. We'll try this for an actual operator rather than just a matrix. So let's just start with psi, some function, and let's start with the what we're going to call a unitary operator, u, e to the I theta. So in other words, this is multiplication by e to the I theta, some complex rotation. So looking at the inner product of that phase rotation, the definition of u psi against a phi as an inner product, we should all feel pretty familiar with this now, is we're going to integrate psi against phi star, except when there's a u in front, we have to multiply psi, right? The definition of u, we multiply psi by e to the I theta. Now the question is the adjoint. Recall, adjoint is the price I pay for moving operator through inner product. So if I move this operator, u, through the inner product and I want to put it against phi, then the e, that's just multiplication, so that can definitely move right over against phi. I have psi e to the I theta phi dx, d star, there's a star there, phi star. But then I need to pull it inside of the star. That's kind of the tricky thing when it comes to these inner products on these other spaces. So the tricky thing of these inner products on these other spaces is they go underneath a conjugate. And to do that, to pull this e to the I theta underneath a conjugate there, the price I'll be paying is giving a little conjugate to e to the I theta, so it becomes e to the minus I theta. So if I scroll down now, we can see that pulling the conjugate out, we end up with e to the minus I theta. So this is pretty straightforward. Like a linear operator should have an adjoint that feels similar to our matrix. So a conjugate transpose here. We don't really transpose a single multiplication, and so because of that, all we're doing is taking the conjugate to recover e to the minus I theta. So moving on to the next section then, we're talking about Hermitian operators. I'm not entirely sure that we've covered this with matrices yet, but you can also refer to stuff as Hermitian matrices, or self-adjoint, or the adjoint of the matrix is equal to itself, right? So that's what self-adjoint means. So Hermitian matrices are the matrices whose adjoints are equal to themselves, or conjugate transposes are equal to themselves. And the nice thing about those matrices is that that we have a very beautiful theorem about these matrices, which says that the eigenvalues, right? So if I have a matrix whose conjugate transpose is equal to itself, the eigenvalues of that matrix are all real. Okay, so necessarily real eigenvalues. And then if they're distinct, I gain orthogonal eigenvectors. So you gain orthogonality for free. And maybe I'll write this down on the side. So given a matrix for which the adjoint is equal to itself, all eigenvalues are real. They're real numbers. And all eigenvectors, parentheses, corresponding to distinct eigenvalues, are orthogonal. And orthogonality is a pretty strong condition, right? And it's a very nice condition. And what it allows us to do in many of these cases with Hermitian matrices is construct a basis of orthogonal eigenvectors. And so this is a really, really powerful theorem that lets us do some really strong things with Hermitian matrices. And ideally, we can get a similar flavor. There's a proof there that I won't go through. Ideally, we can get a similar flavor for operators, right? There's a big idea where we want to do something similar with Hermitian operators. And we certainly can. So how do we define a Hermitian operator? These are the operators. So Hermitian operators are also self-adjoint. Meaning that if I compute the adjoint, L psi against phi, that's equal to psi of L phi. I don't have to pay the price of like a conjugate transpose, or if I do pay the price of a conjugate transpose, I recover what I originally had anyway. So these are the operators which have this sort of a property, and in fact the theorem directly extends to infinitely many dimensions. I necessarily have real eigenvalues. Keep in mind the eigenvalue of an operator would just be something like L psi equals lambda psi, or you can think along the lines of your Schrodinger equation, H psi equals E psi. So those eigenvalues are necessarily real still, as long as I'm Hermitian. I have real eigenvalues. And in fact, if they're distinct, then the corresponding eigenfunctions, right, are infinite dimensional eigenvectors or eigenfunctions. Those are necessarily orthogonal in whatever sort of inner product space I'm looking at, right? And the proof is exactly the same as what we had above here, where you just basically use the property of self-adjointness and you can immediately recover orthogonality and real valued eigenvalues. So jumping down to the Laplace operator, I'm gonna head over to the whiteboard to make this a little bit more clear. Let's recall our Laplace operator is two derivatives in space, and there's a negative sign out front. And we're going to think about the free particle in the one-dimensional box. Okay, so jumping over to the whiteboard, let's say free particle in 1D box. The space that this is working in, the function space is L2 of 0 to L, which is, pretty common. We're very used to that now. It's actually endowed with boundaries equal to 0. That's an extra part that's not usually included in L2 of 0 to L, but in our one-dimensional box, since our sides are considered infinitely tall, the boundaries have to be fixed at 0, and I think you remember this from last semester. But that's what gives us self-adjointness here. So let's show that. Let's show that negative d squared dx squared, aka the Laplacian, is self-adjoint. And you're often going to hear this word from me, self-adjoint, instead of Hermitian. Just think that they're the same, right? Hermitian and self-adjoint are the same thing. But let's show that that operator is self-adjoint. Well, we're going to compute the inner product of psi against phi, and then we're going to try to find the price that we have to pay for moving the derivative onto phi. So recall the inner product, 0 to L. I'm going to have two derivatives on psi against phi. And by integration by parts, for those of you who don't quite recall integration by parts, I define this as dv, I define this as u, and we recover uv minus integral v du, which I suppose in this setting is uv would be like phi negative d dx psi minus, which an extra negative, integral v du will be d dx psi. Du now is d dx phi dx. So that's integration by parts, one step. And because we are 0 at the boundary, this is 0. Because particle in a box, boundary. So we get away with the boundary conditions being 0 here, which is useful. And then we're going to run integration by parts on this one more time. This is going to be called dv. This is going to be called u. And where does that send us? It sends us to, once again, uv. So I have d dx phi against psi minus integral psi v, which is v du will now be d squared dx squared phi dx. And because we're in the particle in a box, this term is also equal to 0 thanks to those boundary conditions, and we end up with negative integral 0 to L psi against d squared dx squared phi dx. And all of you recalling what is the inner product on L2, this is exactly the inner product of psi with negative d squared dx squared phi on L2. And so we've just computed our adjoint, right? We've computed the price to pay for moving this operator to the right. And it turns out that the price we paid was negligent. It didn't exist, and there was no price to pay to move it over, which means that we are self-adjoint. That's the definition of self-adjoint here, which is very useful, right? Because it's the same thing. So jumping back to the book, we have that the Laplacian is self-adjoint, and actually jumping back to the theorem, that tells us some very important things. It tells us that our eigenvalues are purely real, and it tells us that distinct eigenvectors or eigenfunctions are orthogonal. And so if we jump down a little bit to, last semester you calculated the eigenvalues and eigenvectors of this operator. You got that the eigenvalues were these energy levels and the eigenvectors were the signs, right? The different frequencies of sine. But what we gain for free from the theorem, so for free from this theorem, we know that the inner product of sine n pi x over L, comma sine m pi x over L, so two distinct eigenvectors here, we know that the inner product of those two is 0. And we get that for free from the theorem. That's really useful because once we have orthogonality, then projections become very, very easy on all of this. There's one last little thing about the Poisson equation here, which I won't quite cover, but it's about inverting the operator L. So you can read that if you want to. Anyway, that's all I have. I'll see you in class. Bye.